This is our new topic, contingency table. We are still doing hypothesis testing. In this particular section, we are going to use table to do the hypothesis testing. So, we have given data and in 2 by 2 table, and we present a method for conducting a hypothesis test of the null hypothesis that the row and column variables are independent. So that is our goal. So the data given in the table is called contingency table, a two-way frequency table. Okay, and there is a row data, there is a column data. A table consists of frequency counts of categorical data corresponding to two different variables. Frequency count, remember, one variable is used to categorize rows and second variable is used to categorize column. And our goal is to test those rows and column variable independency. In a test of independency, we test the null hypothesis that in a contingency table, the row and column variables are independent. That's our null hypothesis. And alternating hypothesis is dependent. So objective is conducting a hypothesis test of independence between the row variables and then column variables. So these are the notation we use. O represents the observed frequency, E represents the expected frequency, R represents the number of rows, C represents the number of columns. And then these are the requirements we should check before we do this hypothesis testing using contingency table. The sample data should be randomly selected. The sample data are represented as a frequency counts in a two-way table. For every cell in the contingency table, the expected frequency E is at least 5. Okay, observed frequency could be less than 5, but expected frequency should be at least 5. So these are the requirements, and these are the two hypotheses. These are the way we write. The null hypothesis is the row and column variables are independent, and then alternating is they are dependent. So this is called chi-square test, and this is the symbol for chi-square, and this is how we calculate. This is the formula for calculating the chi-square, and this is the test statistics. Like before, we used to calculate the t test and z square test and a g value t test. Here it's a chi-square test, and this is the thing we are going to calculate using this formula. But instead of using this formula manually, we use technology. Okay, so don't worry about how to calculate this value. So here you can see that it's a difference between the observed value minus expected value squared divided by the expected value, and this is how you calculate the expected value. Expected value can be calculated for any cell value by row total times column total divided by grand total. But as I mentioned, we're going to use technology to calculate this the g-square test, not the g-square, a chi-square test. Sorry, it's a chi-square test. Okay, chi chi-square test. This symbol we read as a chi-square test. Okay, and then finally we calculate the p-value and we compare the p-value with the significance label as usual, and then we make our decision. We can also calculate the critical values. For the critical value, for the degree of freedom, this is the formula we use, r minus 1, which is the number of rows minus 1 times number of columns minus 1. And always keep in mind, test of independence with the contingency table are always right tail. What does that mean? Let's say you have observed value and then expected value O and E, and observed and expected value are close in the case of when chi-square value is small and p-value is large. And then observed value and expected value are far apart if chi-square is large and p-value is small. Okay, so that's the requirement. But remember, one more time, we create two hypotheses, null hypothesis and alternating hypothesis. We calculate the chi-square by using this formula, but we use the technology. We calculate the p-value by using the same technology, and we compare the p-value with alpha. And then based on the value with this alpha means significance label, if p-value is less than alpha, reject the null hypothesis. If p-value is greater than alpha, failed to reject the null hypothesis. So we are going to do the same thing. Let's look at some example from this section. Table lists result from an experiment designed to test the ability of dogs to use their extraordinary sense of smell to detect the malaria in sample of children's socks. Based on the data presented at an annual meeting of the American Society of Tropical Medicine by principal investigator Steve Lindsay, the accompanying information shows that hypothesis and TI-8384 plus calculator result for the experiment assume that the hypothesis test requirements are all satisfied. So this is the contingency table, and this is the result from technology. There is a chi-square, there is a p-value, and there is a degree of freedom. So now, what is the test statistics? In our case, for this one, the test statistics is always chi-square, which is 19.49, 19.49. So click the answer. Nice work. What is the p-value? As you can see here, there is a e to the power -5. That means move this one 5 position to the right, and after doing that, if you round it to the 3 decimal places, then it would be 0. Make sense? Okay, so check answer. And now you have to compare the p-value with the significance label, but since the p-value is 0, no matter what significance level you want to test, p-value is always less or equal to that significance level. So that means p is less or equal to alpha. Reject the null hypothesis. Reject the null hypothesis. So which one is the answer? There are two options. Reject the null hypothesis of independence between whether the dog is correct and whether the malaria is present. Reject the null hypothesis. Okay, so this one is the right answer. So if you reject the null hypothesis, does that mean independency imply that dogs are good at identifying malaria? No, we cannot say that. We just say that based on this data, we reject the null hypothesis. So the answer is no. The data suggests dogs are not good at identifying. No, it is possible that dogs are wrong significantly more than they are correct. So rejecting null hypothesis does not mean that you have the opposite answer. Go to the next problem. Let's say this is the data we have given. This is the contingency table. We need to do hypothesis testing. So this table, as you can see here, was the challenge to the call successful? Okay, so what is the problem here? The accompanying table shows results of challenge referee calls in a major tennis tournament. Use a 0.05 significance level to test the claim that the gender of the tennis player is independent of whether a call is overturned. So the gender and then call, they are independent. That is what we would like to check. So our null hypothesis is the gender of the tennis player is independent of whether a call is overturned. So the only options we have, let's say the D1, the gender of the tennis player is not dependent. So this is the only option we have available where the null hypothesis is independent and then alternating hypothesis is not independent. So now after that, how do you find this test statistics? You just copy your data in the StatCrunch. Now this is the data. Just name this variable. Let's say this is the variable 1. Now we would like to go here and click the table. Remember, it's a contingency table, and this is not the data actually. This is actually summary of the data. Okay, these are the frequency. So we are using summary of the data. Now columns, among these 3 data, we're using this column, successful challenges and unsuccessful challenges. So just highlight successful and just select these 2 for the column, and for the row select the variable 1, which is this is the row. Okay, row labels. Okay, variable 1, men and women, and this is the column, successful challenges and unsuccessful challenges. Now what do you want to do? Forget about everything else, just go to the hypothesis test, which is the chi-square test, and the confidence level is, because significance level is 0.05, the confidence level is 0.95. just compute and it gives you everything. Chi-square is, this is the value, 29.58. Okay, so the value is, round it to the 3 decimal place. If you round it to the 3 decimal place, it would be 29.58. So it's a 29.58. There is a 0, so you don't have to type that 0 here. Okay, what is the p-value? The p-value is, as you can see here, this is the p-value, which is less than 0.0001. If you round it to the 3 decimal place, it would be 0. So remember, the p-value is less than alpha, so we reject the null hypothesis. So as you can see here, the p-value is less than alpha, we reject the null hypothesis. So what are, which one is the right option here? There is not sufficient evidence to warrant rejection of the claim that the gender of the tennis player is independent. No. There is sufficient evidence to warrant rejection of the claim that male tennis players are more successful. No. There is sufficient evidence to warrant rejection of the claim that gender of the tennis player is independent of whether a call is overturned. That's the rejection of the null hypothesis. Okay, let's go to next problem. Which of the following is not a requirement conducting a hypothesis test for independence between the row variable and column variable in a contingency table? So if you go back to your notes, there are 3 requirements you have to fulfill. The sample data should be randomly selected. The sample data are represented as a frequency counts. And then for every cell in contingency table, the expected frequency is at least 5. The expected should be at least 5. So as you can see here, the sample data are represented as a frequency counts in a 2-way table. That's right. For every cell in the contingency table, the expected frequency is at least 5. That's right. But this is not required. So that's not requirement.